Okay, are you able to hear me now?
Yes, sir.
Okay, there was a connection problem. Today, I am going to introduce the concept of transfer function and some basic rules of transfer function, followed by the modeling of an electromechanical actuation system. So if you, okay, I will give you some break in between so that continuous staring on the screen is a bit difficult. Here I am taking the presentation from another link that also.
Excuse me, sir, your screen is not visible.
Not visible. Okay. One minute. I will make it. Now is the screen is visible?
Yes, sir.
Yes, sir.
Okay. So when the connection got broken, this screen share mode also went. That's okay. I'm sorry. So I'm going to discuss about the concept of transfer function today. This slide is taken from another person. That is why it is somewhat generic, but no problem. It is giving something more than what is required. This is explaining with respect to some general system dynamics. Yesterday we were talking about two types of system. One is static system, another is dynamical system. And I told that in dynamical system, the speciality is there is provision to store energy. Or we can say that there are some internal states of the system. Internal states. Simple example, our mind is having some internal states which cannot be changed instantaneously. Similarly, a mechanical system which can store potential energy or kinetic energy are having states corresponding to the current position as well as state corresponding to current velocity. Because in a spring, potential energy is stored as half kx square, whereas in a mass, the kinetic energy is stored as half mv square. So wherever the energy storage comes, the variable, time domain variable, either x or v or similarly I in a magnetic storage media, or voltage V in a electrostatic storage media. So such variables are known as states of the system, internal states of the system, that always is associated with some form of energy storage. So the title of this slide is Zero State Response. What does it mean is the system is starting from rest with zero values for the corresponding internal states. For example, a mass attached with a spring, it can store both kinetic energy and potential energy. So if such a mass spring system is starting from zero position and with zero velocity, then you can say that it is starting with zero state value. Two states are there, both are having zero values. Similarly, an inductive RL circuit starting with zero current, or an RC circuit starting with zero voltage across the capacitor, all these correspond to zero state. Now, we are only concerning about zero state response, because transfer function analysis is meant for zero state condition. So under that condition, what will happen? They define transfer function, but in general, the system output YT is due to two parts. One part due to zero input response, another is zero state response. Now we are considering only zero state response, zero state response. Under zero state condition, now all our discussions are with zero state only. That is, our dynamical system is starting from ideal rest. That simply you think. Or for example, you are waking up in the morning after forgetting everything what has happened during the previous day, or all the dreams you have forgotten, and with the blank sheet in your mind, if you are wakening up, and if an input is given to you, how you will respond to that. Similarly, a mass spring system, it is in rest condition as well as it is under zero position. Zero position means the spring is in neutral state. It is not in compressed or extended condition, neutral state. Then if you give a force command, how the mass spring system will respond. That's the meaning of that. Under that condition, YT, it is the response. Its form is called YS. This is the normal notation, YT and YS. Similarly, XT, here X refers to the input. Input is here given as XT. XT corresponds to Laplace transform of Xs. I know that you all studied Laplace transform, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So we assuming that you are familiar with the Laplace transform properties. With that background only, I am going to teach you. So the Laplace transform, the differentiation theorem in the Laplace transform says that the rth derivative of yt with respect to time t is having a Laplace transform of s raised to r into ys, assuming all initial values of the up to r minus 1 derivatives of yt, including y0, are 0. It's starting from rest. Here we are talking about, you can say, an r-dimensional system. Their ideal rest means its position yt at t equals 0 is 0. Similarly, the first r minus 1 derivatives are also starting from 0 value. Under that condition, this Laplace transform pair is correct. Similarly, with respect to input also, you can say if x0 is 0 and first k minus 1 derivatives of x are also having 0 value, then you can have this Laplace transform expression. Applying that rule to a system, a simple system, it is showing a simple dynamical system. Let it be represented by first derivative of yt plus yt is equal to xt. This corresponds to an RC network that we will see how to model. So xt is the input, yt is the output, and y dash t is the first derivative of output. This is the dynamical equation. Here R is equal to 1 ohm and C is equal to 1 farad. Under such condition only this equation will be correct. And if you differentiate, take the Laplace transform from both sides, you will get SYS plus YS is equal to X. Here we assume that the initial condition of Y 0 minus, that is just before 0 time, just instantaneously, infinitesimally small negative time. If it is equal to 0, then corresponding to that, otherwise there will be a y0 term also will come. If you are taking the Laplace transform of the first derivative, that need not be taken. That is why we are able to finally, you can write all these ys common x's, then you can take the ratio ys by x's is equal to 1 by s plus 1. This is the transfer function of the first order low pass system. Hs is called the transfer function. We will come to details further.
Sir, one doubt.
Please.
Yeah, Sriram, you can ask this.
Sir, I was asking, sir, what is this linear constant coefficient differential equation and how did we arrive at that?
Okay, how we will arrive at this equation? That is your question.
Yes, sir.
Okay, let me see now. Let me see if there is any practical example given in this slide, because I have not made the slide, but I will show you in that when we talk about our electromechanical actuation, there I only made the slide, there I will show you. Let me see, is there any example is there? But here itself I can say, what does it, if you can mentally remember. T is corresponding to input voltage. This is an RC series circuit, RC. XT is the input voltage and YT is the output. There is voltage drop across the capacitor and Y dash T is the voltage drop across the resistor. So you just consider, you know that V is the voltage drop equation, Q equals CV, you know, Q equals CV. So V is equal to Q by C. Okay, you can remember. V is equal to Q by C. And here
Yes, sir.
C is equal to 1 farad. So you'll get output voltage V is equal to Q, charge across 1 farad capacitor. Okay. Now the current passing through the capacitor is dq by dt. That is the derivative of yt, y dash t. Okay.
Yes.
That current is applied, is passing through as 1 ohm resistor, which will produce a voltage drop of y dash t across the resistor. So CR series, the applied voltage is equal to voltage across the capacitor and voltage across the resistor. This is the modeling, but unfortunately, I have to, the main problem here is software problem. This particular P, I am using Adobe Reader. There the pen is not available. If I go to Microsoft, the Edge, there the shifting of the slide is not possible. So I will come back. Okay, if you got out, I will explain. Definitely, your teacher will be teaching, Rajesh sir will be teaching all these things. I am only going through an introduction, but it is available in textbooks. Okay. For time being, you pardon me because I am in online mode. Okay.
Yes, sir, I got.
Okay. Okay.
Sir, I also have now.
Yeah. What is that?
In the previous slide, the
Ah.
second column, which was written for xt, yeah, this one. So the second line, the derivative, the kth derivative of x is equivalent form in Laplace is s to the power k into x of s. This I think is it true only? It may or it may not be true for zero state response, right?
So here we assume that all the states are starting from zero. State
Yeah.
means this here only thing is that here we are mixing two things actually. Uh, here we are taking only the derivatives of the output. Okay.
Yeah, but xt in this case refers to input, right?
State means something which I have not defined. I only verbally told. Wherever some energy storage is there, there are some internal states. But in this equation, they are only showing input and output. Actual state is represented by another variable. Normally, it is represented by xt and input by ut. But unfortunately, in this particular slide, because I took from somebody else, they are representing the input by xt. So there is a problem with convention. So zero state means internal states are zero value. But definitely, if the first are derivatives of output, here the system is having r states. And one of the state is yt itself, and the first r minus 1 derivatives of yt also can be considered as states. In that sense, you can say that all the states are starting from zero value. That is called zero state response. That will provide this particular equation correctly. Okay.
Yeah, the equation of y is fine. That equation for x, I was not sure. How do we obtain only by the condition of zero state? Is it so?
This okay, you are right. This is x is corresponding to input. Now,
Yeah.
what they say is that the input is also starting with, that is, it is not starting with a finite value of its derivatives. Because otherwise this equation will not be correct. The input is also having this particular restriction. Otherwise, what will happen is when you write this equation, there will be terms containing the initial values of the derivatives of the input. So you cannot simply take the ratio between the Laplace transform of output, Laplace transform of input. So we put that restriction for the type of input also. Then only you will be able to take this particular equation. You can just see that in a dynamical system, probably I am coming to such a rational polynomial system. It is called infinite impulse response sort of system, where these things actually come into play. I will show after if these slides are having such a equation. Okay. The point is actually control system is a big topic, and I am supposed to cover all these things with 5-6 class, but so the syllabus of avionics is set in such a way that lab as well as control theory go in parallel. Aerospace people have changed it. First we will complete the entire theory, then only lab comes. But unfortunately in avionics, the management has not agreed for that. Otherwise, you should be taught this in detail during fourth semester, and lab should occur only subsequently. So here I am jumping because if I teach everything in a minute level, I cannot cover the lab theory and lab. Lab is only 1 credit, control system theory is 3 credits. That also you keep in mind. So I am giving only a rough framework. Details will be covered by Dr. Rajesh Joseph Abraham, and also texts are also there. But you can ask me doubt. Any doubt, I am always happy to hear it, but only time is the constraint. Okay. Yeah, so how will define transfer function? HS is called the transfer function because it describes how input is transferred to the output in a transform domain. Yes, domain. So the very speciality, the most important speciality of going to yes domain is that assuming zero state condition, then the Laplace transform of output and Laplace transform of input are related through a particular transfer function, HS. HS is normally a rational polynomial function in terms of S. So a compact form of representation between input and output is able to be obtained. And YT can be obtained as inverse Laplace HS by using the convolution theorem of Laplace transform. You can get all these things. And one small introduction. Hello. ഞാൻ ക്ലാസ് എടുത്തുകൊണ്ടിരിക്കുകയാണ്. ഓക്കെ, ഒരു അരമണിക്കൂർ കഴിയും കേട്ടോ. So transfer function, there is a definition for transfer function. So these are another way to write the input-output response. You can see the difference. See, in time domain, you are writing yt is equal to ht convolution xt, where in frequency domain, you are writing ys is equal to hs into xs, where hs, capital Hs is the Laplace transform of small ht, and all other things are Laplace transform pairs. Now the convolution is a complex, it is an integration operation. It is only, symbol-wise it is simple, otherwise it is more complicated. But here it is a simple multiplication. That's the beauty of going to yes domain. Now, HT is having a beautiful interpretation. HT is known as the unit impulse response of the system. You know that Laplace transform of unit impulse command is unity. You know that. Laplace transform of del t unity is called del t. Its Laplace transform is unity. So if you give a unit impulse command to this system, suppose XS is the Laplace transform of the unit impulse command, then XS is equal to 1, right? If you are giving xt as an impulse command, XS equals 1. So ys is equal to hs. So the interpretation of hs is, it is the Laplace transform of the unit impulse response of the system. This is the interpretation will come. Hs equals Laplace transform of ht. Okay, then we will go to some examples of Laplace transfer function. This is the definition of Laplace transfer function. There are other definitions are there. You might have seen minus infinity to plus infinity xt e raised to minus st dt. But here we assume that all signals are causal. That is, we are not considering t minus. Negative types are not considered. We are living in physical world. So we always, any experiment when we start at 0 time onwards. So we assume that all the signal for negative times are 0. So there is no point of integrating from negative time onwards. That is why it starts from 0 minus 2 infinity xt e raised to minus st dt. And assume input xt and output yt are causal. That is, they are all existing beyond 0 time only. Ideal, now we take some simple example of transfer function of different linear time invariant element. The simplest dynamical element, yesterday we were talking about dynamical system, right? So dynamical system says that the current output depends only on current input. Sorry, that is static system. So a dynamical system is one where the current output depends on previous inputs. So under that category, the simplest element is a delay element T. If T equals 0, capital T is equal to 0, then it will become a system. The instantaneous output depends on instantaneous input. Otherwise, this is the simplest thing. And you can represent the time domain expression for delay as yt is equal to xt minus capital T. And if you take the Laplace transform of that, you will get ys is equal to xs e raised to minus st, or transfer function is e raised to minus s capital T. This is not a rational polynomial function. It has infinite terms if you expand, but you can approximate by finite number of terms. Okay, this is the first step. Second element is ideal integrator with y0 minus 0. The integrator, you might have the implementation of integrator using an op-amp, operational amplifier. You have studied, am I right?
Yes, sir.
Okay. There, if you assume that the op-amp, there is a capacitor across the op-amp, and the capacitor initial charge is equal to 0, that corresponds to initial voltage output of the integrator is 0. Under such a condition, you can represent the integrator like this with xt as the input, and if you take the Laplace transform and assuming 0 value of the initial output, you will get transfer function of integrator as 1 by s. So this is next simple dynamical element. The most simple dynamical element is simple delay. The next complex one is 1 by s. But opposite to that, there is another element, ideal differentiator. Since we consider ideal integrator, we consider ideal differentiator also. There, yt is dx by dt, and we assume this initial condition. Then you can take the Laplace transform and get. So it is just an inversion of this integrator. So this is the time domain representation of an integrator, time domain representation of a differentiation, but its Laplace transform is 1 by s here, it is s. Now there is some symbolic operations. If you cascade to linear time invariant system, assume input xt and output yt, there are two systems are cascaded. Here we have cascaded first integrator followed by differentiator. Next one is first differentiator followed by integrator. You can see that the input is same as output because doing inverse operations. Here also, so irrespective of the order in which these systems are connected, you will get the same transfer function. So the overall transfer function you can obtain, first you give xt, you are getting integral of x tau, then we are differentiating it. So integration and differentiation will cancel, just like that 1 by s and s will cancel to produce 1. Then common transfer functions are simple, a constant term. That is nothing but static system. Here when we constant means say 1 to any constant value. Another is a polynomial. Polynomial in terms of s, Laplace operator. For example, as plus b, as square plus bs plus c, like that. That is another common transfer function. it is having finite impulse. What does it mean? Is if you give a unit impulse command, its response will vanish within finite time. Another type of transfer function is ratio of two polynomials. The numerator, there is a, say, as square plus bs divided by cs cubed plus ds square plus es plus a rational polynomial. It will have infinite impulse response. That is such a system. If we excite with an impulse command, the time domain response output, it will go up to infinite time. It will go towards zero or diverge, but it will take infinite time to settle. Such a system is called infinite impulse response system. And some rules, common rules or block diagram rules. If we have xs as input, ys as output, hs as a transfer function, h1, h2 can be two blocks together, can be put as h1, h2s, and you can represent a two linear time invariant system in parallel, and their outputs are, if their outputs are added, they can be represented by a single block with h1s plus h2s. Another is the feedback connection. Yesterday we were discussing about that. So in this condition, this is a very peculiar situation. You know that the cause effect, they are mixed together. Here all you can say that this xs is the cause and ys is the effect. But here how will say? Here also you can say that xs is the cause, ys is the effect. But if you look on this point, then es not only depends on the external, es depends on the output ys. So you can say that es is the effect of both xs and ys. At the same time, ys is the effect of es. Goes to an algebraic equation where the effect is coming on both sides of the equal sign. So the effects we have to segregate at one point, and hence the division comes. So it is another interpretation of division. In electronic circuit, you might have heard of bootstrap circuit. This is something like output is if you are pulling your own leg, what will happen? You are pulling your own leg, but you are pulling using your hands. Your hands is resting on your legs, and at the same time you are trying to pull your own leg. Finally, you will rotate. Something will happen. Similar to that, this is a similar situation of this feedback network, and finally it will lead to a division, gs by 1 plus gshs. This is the then cascade and parallel connections. Okay, we have shown these are simple rules. Feedback connection, whatever we studied, same thing. They are giving the algebraic derivation. How you are getting gs by 1 plus gshs. Here the expansion is given. If you are giving ys as the output, ys is equal to gs into fs minus hs. Here hs ys. So here you can see that the effect is a function of the cause and effect. Effect is the function of the original cause and effect. This is the bootstrapping action I was telling. So you have to segregate all the effect ys terms together at one point, and this is the cause term, and you are getting the transfer function. Any doubts?
Yes, sir. Excuse me.
Okay.
Yeah, sir, can you
Ah.
please explain this feedback system? How did we get this equation once again?
This equation you are telling?
Yes, sir.
You see, combining it, say, unfortunately, I will reduce the, okay, now it's visible, the complete portion, right?
Yes, sir.
You can see Fs, Ys, Gs, Hs is a subtracting element. Is there any confusion with respect to block diagram?
Yeah, yes, sir. Just how is this feedback system working? Can you?
Okay, how does it work?
Yeah.
One method is you have studied op-amp circuit, right? You have studied non-inverting and inverting amplifier configuration using op-amp circuit.
Yes, sir.
Okay.
So we get negative feedback.
You have studied that. So that is a one simple example of simplest example of such a thing. But you assume that using op-amp circuit, you can realize summer, right? You have studied summing circuit using op-amp.
Yes, sir.
Now you assume that this is a summer circuit, but only thing, the polarity, an inverter also is placed prior to one of the summing inputs so that this can be realized using a op-amp summing circuit with an inverter in the feedback path. Okay. Now the output is taken, and in the op-amp, the ideal case, you know that the output impedance of op-amp is 0. Okay. That means whatever value of current you are taking from the output of that, that will not affect its transfer function. The op-amp's property will not be affected. So an ideal op-amp is having infinite input impedance and
Zero.
zero output impedance. So because of that, whatever voltage if you are taking, you are giving to the op-amp, it will not take any input current, and whatever current you are taking from the op-amp will not drop any output voltage. This is something similar to that only. This is actually a mathematical representation, but you assume that you are applying a signal, two signal to a summing block using op-amp. Okay, that will give the output as a sum of that. That is given to another dynamic block. This GS is a plant controller, everything can be either electrical or mechanical. Then only thing is that it will not, if you are driving the system with an ES, the value of ES will not be changing. That's mean. That is, the circuit or the system will not load the source of this signal so that the signal value is protected. If you consider such a case, it is easy to understand. Then you take the output and feedback. So this is the system. But any practical system you can represent. That's why in the second part of this lecture is actually modeling an electromechanical system. There I am explaining all the physical elements. You will clearly understand it. So this is only a mathematical construction to represent how the feedback network works. Okay.
Yes, sir. Thank you, sir.
Okay, next portion is the stability is the next very important portion. When you consider the stability of a dynamical system, there are different norms for talk stability. Here, we are considering generally the linear time invariant system. So we talk about bounded input, bounded output stability. That is, if the system is starting with the zero state, all the state values are 0. If you are giving a bounded input to the system, output will be bounded. The steps are, first, we are taking a peculiar case to differentiate between the 0 and the response due to finite initial state as well as response due to input. You consider such a system. 1 by s minus 1 is equal to s minus 1 divided by s plus 1. Assume that this is the system transfer function. But you can see that mathematically you can cancel this s minus 1 and s minus 1, leading to 1 by s plus 1. This system, if you start with all 0 initial condition, then it is bounded input, bounded output stable. If you, for example, if you give a unit impulse command to this system, the response will be e raised to minus t. That is, as t tends to infinity, it will diode from unity towards 0. In another way, we can say that the root of the denominator is minus 1. It is the left half of S plane. So such a system is called bounded input, bounded output system. And its requirement is all the poles of Hs, that is the transfer function, should be in the left half of S plane after removing all common factors of the transfer function. Here we are removing all common factors, and after the reduced form of Hs you take, and if all the poles of Hs means roots of the denominator. If they are in the left hand side of S plane, here the pole is at S is equal to minus 1. It is left to the imaginary axis by an offset of 1. So it is a stable system. But this is an example where even though bounded input, bounded output point of view, it is stable, but it is asymptotically unstable system. That is because of the prior to cancelling, there is an s minus 1 term is there. So if there is any disturbances we are giving to the state, internal state, that will diverge, but you need not have to worry about that. That are all advanced part of the stability that you will study in the control system class. That internal stability condition, stability based on 0 input solution. That's what I told you. The requirement is there we are not cancelling any roots. All the system roots will be there. Then it is asymptotically stable if and only if all the characteristic roots are in the left half of S plane. Roots can be repeated or non-repeated. So if you consider an S plane, if all the poles of the system transfer function prior to any cancellation, all are in the left half of S plane, means it will be asymptotically stable. Asymptotic stability means as t tends to infinity, the output tends to 0. That is meaning of asymptotic stability. Then unstable. So we are now defining not the BIBO stability. It is other classification of stability which takes care of the internal cancelled cases also. So without cancellation itself we are handling. It can be asymptotically stable, it can be unstable, it can be marginally stable. Asymptotic stability means all the roots of the denominator without any cancellation, all should be in the left half of S plane. Unstable if and only if at least one characteristic root is in the right hand plane. Right half of S plane, or repeated roots on the imaginary axis. For example, say imaginary axis roots means S is equal to plus j omega 1, S is equal to minus j omega 1. They are not repeated. But if you have two roots on plus j omega 1 and two roots on minus j omega 1, then it will be unstable. If you have two roots at the origin, it will become unstable. That is 1 by s square, for example, is unstable. So these are all unstable conditions. Then marginally stable, if and only if there are no characteristic roots in the right and some non-repeated roots can be on the imaginary axis. Actually, I should have shown a plot of how the poles are segregated, but it's available textbook. This slide is not showing yet. Okay. The frequency domain interpretation I will teach in a better way in my lab class. This may be a bit complicated. You don't worry about this. I am giving a easier interpretation of that. So this is the end of the first portion of the lecture. Now I will give you some free time. You can take some water. When can you come back? How much interval you want?
Sir, can I ask a question?
Yeah, you can ask question.
Sir, can you explain again what is marginally stable?
See, marginally stable means simple example, if you stability in very general sense means stability, there are different norms of stability. Since you asked this question, I am going in a more wide perspective of stability. One is stability associated with an equilibrium point. If you excite or disturb the system which is in an equilibrium point, if it will come back to its equilibrium by its own, it is called a stable.
Stable equilibrium.
If it diverges away from the equilibrium point, it is called
Unstable.
but it neither come back nor diverges, but it simply oscillate around, rotate or move around the equilibrium point with neither diverging nor converging. It can be called as a marginally stable system. That is a physical way to interpret. Its corresponding mathematical requirement only I told. If you take assume the system is a linear time invariant system, it will have a transfer function. Then you take the poles of the transfer function without any internal cancellation. Okay. Then if one requirement is there should not be any poles in the right of a S-plane. If there is one pole in the right of S-plane, system is unstable. But there can be poles on the imaginary axis, but the requirement is it should not repeat. Repeated poles at the same position on the imaginary axis is not allowed. If they are repeating, these two, I told you now, it will neither converge nor diverge. Such multiple trajectories will be there. They will interact and finally they will diverge. That will happen. So if the roots are not repeating, but there can be finite number of roots on the imaginary axis. Such a case is called marginally stable system.
So it means no poles on right hand side of S plane and no repetitive roots on the imaginary axis.
Exactly.
So, but then wouldn't it be a case of asymptomatically stable because there also like there is no root on the right hand side and like there may be non-repeated root also.
No, for asymptotic stability, all roots should be in the left half plane. Because say, when you expand the inverse Laplace transform for an impulse response, there will be terms like some k1 into e raised to minus t by tau 1 like that. So all terms should be exponentially decaying. Then only the total response will decay towards zero as t tends to infinity. If at least one root is there on the imaginary axis, they will not, the e raised to minus t by tau, that term will be absent. Instead of that, it will be some e raised to j omega t, which will give to sinusoidal response.
Yes, sir.
So, okay, I will give a small break. We'll start at say 350, right? 350, okay?
Yes, sir.
Okay, take some rest. 350 we'll start. Yes, madam, എന്താണ് വിളിച്ചത്? ഞാന് വീണ്ടും ഒരു മെയില് ഐഎസ് വന്നായിരുന്നു. ടാസ്ക് തന്നെ എഴുതി വിടണമെന്ന് പറഞ്ഞു. അങ്ങനെ ഞാൻ എഴുതി വിട്ടത് കേട്ടോ. അതിന് മിക്കവാറും കുഴപ്പം വരത്തില്ലെന്ന് ഞാൻ പ്രതീക്ഷിക്കുന്നു. കാര്യം ഇപ്പോൾ ആ ബോൾ പൂർണ്ണമായിട്ട് നമ്മുടെ കോർട്ടിലിട്ട് തന്നു. ഓരോ സെൽഫുകാർക്കും തീരുമാനിക്കലേക്ക്. So, okay, shall I start the next portion?
Yes, sir.
Yes, sir.
Okay. Now I am coming to the actual portion of our lab. So far, we are talking about the introduction to control system and some basics. This is the first portion. As I told yesterday, we will be going through various case studies. One part of the case study is electromechanical actuator system. And I'll be giving you the mathematical model of the PSLV fourth stage, PS4 engine gimbal control system. Its values only I'll be giving you. So it is a physical system, and as per the history, it is the first electromechanical actuation system developed by ISRO, even though it is in the fourth stage of PSLV. And it is actually using a brush type electromechanical actuator. I will show you the details of that. First portion is mathematical modeling of armature controlled brush type DC torque motor. Nowadays, all advanced actuator systems use brushless DC torque motor because brush type is having the problem of wear and tear. But as per the history, this was developed very long back. That time brushless technology was not available, and because of that, we have developed this brush type only. And since the system is working, now nobody is brave enough to change a working system because it will affect various other softwares and all. It will produce problem. So this is still continuing. This is a simple example, how or explaining the basic principle behind the electromagnetic motors. You may know that electromagnetic force is the second highest force in the universe. Then the question is, which is the highest force in the universe?
Atomic.
Eh?
Nuclear force.
Nuclear
Correct. The force is inside the nucleus of an atom. That is the highest force. So second highest force is electromagnetic force. And that is used to convert electrical energy into mechanical energy in an electrical motor. So you can say that the magnet is the medium. The magnetic field is the medium by which we are converting an electrical input energy to mechanical output energy. So the size of the motor is very much depending on the ability of the permanent magnet to produce large magnetic field intensity within a given volume. Earlier, in olden times, such magnets, powerful magnets were not available. But nowadays, some special rare earth magnets were developed like samarium, cobalt and all. They will produce large magnetic field flux density for a given volume of the permanent magnet, thereby reducing the size of the motor. And the rule which talks about the electromagnetic force generation is called Fleming's left-hand rule, which states that when a current carrying conductor is placed in an external magnetic field, the conductor experiences a force perpendicular to both the field and to the direction of the current flow. This is the Fleming's left-hand rule shown as a picture. North to south, that is the direction of magnetic field. That is shown by this index finger. Then the direction of current is given by the a ring finger. This is which finger? Middle finger, right? Middle finger. Then the thumb indicates the direction of the force. So it can be easily verified in any configuration. This is called Fleming's left-hand rule. Then I have drawn my own diagram. Again, this is north pole, this is south pole. B represent the flux density. It is a vector. It is directed from north pole to south pole. Then this is a single coil, single current motor coil or armature coil. And the armature coil is supplied from a EMF source, voltage source. But this coil is wound on the cylindrical, this is actually cylindrical shape. I have given a 3D view of that. This is the north pole, this is the south pole. This is one coil wound on the surface of a cylindrical rotor. And the cylindrical rotor is supported on bearings. This dotted line shows the axis of the rotating element or axis of the motor. And while this coil is rotating, then if you give a firm connection from the voltage source to the coil, what will happen? That will get twisted. That is not possible. That is why there is a contact, sliding contact is provided from the voltage source to the coil, and this is called brush. Brush is made of some material called graphite, which is both conducting media. At the same time, it is smooth enough so that it will not produce much wear and tear power, but still there will be wear and tear. This brush is the one which life of the this particular setup. That's why nowadays nobody go for brush type motor. There is other concept called brushless motor. In such a case, the rotating element, coil will not be rotating, coil will be stationary, whereas the magnet only will be rotating. So the magnets will be placed on the surface of the rotor and coil is stationary. And depending on the polarity of north pole, south pole changing, will switch the direction of current through the coil through switching circuit. That is called brushless technology. But anyway, the final equation for brushless motor and brush type motor both will be same. But this is more easy to understand. That's what I the model of a brush type motor. And this is also called armature controlled motor, because this is called known as armature coil, and we are controlling the torque equation or the torque generated through controlling the current through the motor coil. Now the equation for the torque can be given as, see, consider this, this is a better diagram. Consider only a single conductor. This is called one conductor. This is called another conductor. And both conductors are connected together to form a coil like this. And the current flows through one conductor from front to back, whereas the current flows from back to front in the other conductor. But it is not a problem. Their forces will be additive. I will show you. Now you consider only a single conductor, and the force acting is given by Fleming's left-hand rule. You know that if you keep your hand, take your left hand for time being and keep this index finger along north to south and align your middle finger along this IA, then you can see that the direction of the force will be downward. That is, gives the direction of force that will be downward. Now this is called jth conductor, forming an angle of theta j with respect to this vertical axis. What is the effect of this? And what is the formula for FMJ? FMJ is called B into IA. You might have heard of Biot-Savart's law. For this, so many scientists' name may be associated with this. Anyway, simple thing, force is equal to product of flux density in Weber per meter square, length in meter, IA in ampere, then force will be in Newton. This simple expression. This is the force equation. And this force will produce a torque about this axis. How you will get, you can see from here, this diagram. FMJ is acting downwards. The same thing when you see from the front view of this thing. And this axis is represented by a dot. Now the momentum of this force with respect to the center is r sine theta. Theta j is there. R is this radius of the rotor. So this here distance is r sine theta j. So the torque by FMJ about the axis of the rotor is BLIA into r sine theta j. Now, what is the total torque on the rotor? It is the sum of all the torques produced by these current carrying conductors. And one good thing, you need a half divide this in two halves. Say this vertical plane divides the rotor into two halves. Corresponding to any such conductor, there will be an 180-degree opposite conductor such that both will have the same current, both will experience the same magnetic field, but the direction of current will be opposite. Here current goes the front to back, here back to front. Because of that, what will happen? The force direction will be opposite. But the forces are additive with respect to torque point of view. The FMJ produces a torque TMJ here. Now the same FMJ upward will produce the torque in the same counterclockwise direction. Both the forces will produce counterclockwise torques about the axis. So there is no need to integrate throughout the circumference of the rotor. You can only integrate from theta j varying from 0 to pi alone. And then 2 can be taken outside, sigma TMJ. So 2 BLIARA sin theta j, where theta j is varying from 0 to pi. Basically KT into IA. By taking IA outside, all other terms are leading to a constant term KT. Isn't it? 2 is a constant, B is a constant, L is a constant, R is a constant, and sin theta j varying from 0 to pi. Now, how many J's are there? That depends on the resolution of the coil. How close you have wound all the motor coil, it will. So you'll get KT into IA, where KT is the torque constant. A similar expression you can derive for the magnetic or the induced back EMF. So there are two things happening together. One is, if you place a current carrying conductor in a magnetic field, it will experience a force. Similarly, if you move a conductor in a magnetic field such that the conductor cuts the magnetic lines of force, then a EMF will be induced across the conductor. That is electromagnetic induction, force, voltage induction. And the induced EMF is having the formula EBJ. That is consider this jth conductor. Now assume that this is open circuit. We are not giving any external current. Just the coil is open circuit. We are simply rotating the motor with an angular velocity omega m. Okay. And such a velocity will lead to a linear velocity of each conductor, which will cut the magnetic field. Now, if it assume that Vj is the downward velocity of this conductor, Vj, then the induced EMF is given by B into L into Vj, where Vj is the velocity orthogonal to the magnetic field. Already conductor is orthogonal to the magnetic. Now the motion is orthogonal in the other direction to the magnetic field. And Vj you can obtain from omega m into r into sine theta j. Suppose this rotates with an angular velocity of omega m. So there will be a velocity in this direction called omega m into r. Then its component downward you get by multiplying by sine theta j. So you this expression, finally you will be connecting all the coils. Now this is one coil only. The next coil, which is slightly shifted in angle from this coil, will be connected at the end of this coil. So they are additively connected so that all the voltage will be added. Here also again, when in a single coil, the voltage across this conductor and voltage across this conductor will be opposite direction, but they will drive the current in a consistent way through the loop. Here it will be plus minus, so that it will drive like this, and here it is plus minus. Even though these plus minus are reversing from the top to bottom conductor, but along a loop they are additive. So you can get the total induced EMF using this equation. EB is equal to again 2 sigma EBJ. Theta j is varying from 0 to pi. They only consider half of the drum because the other half voltage will be adding. And finally, you will get KB into omega m, where omega m is the only variable. All other things are constants or parameters of the motor. And you can also see that KB is equal to KT. There is KT is equal to B L R sigma sine theta j. Here KB is also equal to B L R sigma sine theta j. So if you are using SI units, both KT is equal to KB. So that gives the motor basic equation. So one equation converts electrical current into mechanical torque, whereas the other equation converts mechanical velocity into electrical voltage. They are dual variables. If you multiply the input portion, the electrical energy is given by voltage input current into input voltage, whereas mechanical power is given by torque into angular velocity. So finally, both will be equal if there is no loss in the coil resistance. That's a equation for this system. Any doubts on this? Any doubts? No. Okay. All are able to follow it? Hearing?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay. Because it is online class, I had to verify, as I am not seeing while I am sharing the screen, that I am asking. Now we go to the next portion. This is a modeling of a motor, an armature control brush type DC torque motor. This is the equivalent circuit of that. This is the armature portion. The brushes are represented like this. We have the applied voltage across the armature coil. Armature electrically you can represent like this. Resistance of the coil in series with inductance of the coil, and that is in series with the back EMF generated. And the direction of back EMF in such a way that it will oppose the very cause producing it. Now the cause producing back EMF is nothing but the rotation of the rod. Which is the cause producing the rotation? It is the current passing through that. So the back EMF will oppose the very cause. This as per the Lenz's rule, and it will oppose the. So we have EA, applied armature voltage. This is the back EMF. And now let me represent the mechanical part of that. Say the rotor, the electrical part only we consider, but rotor, it is a rigid body which is having a moment of inertia that is represented by Jm, and the rotor is supported on two bearings on both sides. So definitely there will be some bearing friction, but now I am considering only the linear part of that. Friction is having viscous damping portion as well as Coulomb friction. Time being, you assume that there is no Coulomb, only viscous damping portion. So it's Bm. Then it can have stiffness also, but that is not considered here. So this is the overall electrical mechanical equivalent circuit of a armature control brush type DC torque motor. Any doubt on this diagram? Okay. Now we can write the equation with respect to electrical part as mechanical part. Electrical equation, applied voltage across the armature EA is equal to IA into RA, that is a ohmic drop, plus LA into DIA by DT is due to the inductance effect plus EB. Straightforward. Or you can say that EA minus EB is equal to IA into RA plus LA into DIA by DT. And there is an expression for EB. EB is equal to KB into omega M. We have just derived the back EMF expression. So this completes the electrical modeling of the motor. Now the mechanical portion can be modeled like this. Tm, we are applying a torque Tm. Tm is equal to Jm into S square plus Bm into S into theta ms. Okay, this will be something new to you. This is how we model mechanical systems. You can probably see, you all have Norman nice, I hope. There, they are giving nicely how we can model a mechanical system having a number. This corresponds to mass or inertia part. Bm corresponds to viscous damping. So a mass damper system modeling, you can just refer. So finally, you can understand that if you are applying a torque Tm across a mass damper, this is the mass or inertia damper. The relation between applied torque Tm and theta m can be given like this.
Sir, what is Bm, sir?
Bm is the coefficient of viscous damping. It corresponds to any viscous damping on the bearing of the motor.
Sir, and Jm is the moment of inertia of the armature?
moment of inertia of the total rotating elements about the axis. So roughly you can say armature. Armature includes the coils. It includes the frame over which entire structure. So whatever is moving about the axis together is called rotor. So moment of inertia of the rotor. In brush type motor, armature is rotating, but in brushless motor, armature is stationary. So the term rotor is better. Moment of inertia of the rotor. Now, we have studied the block diagram algebra. These equations can be fully represented like a diagram shown here. It's a pictorial visualization, always give a better understanding. Here, EA minus EB. EA minus EB is coming here, that if you take the Laplace transform of this, EA minus EB of S is equal to RA plus LAS into IAS. IAS means Laplace transform of current. So you'll get the relation between IAS and EA minus EB as 1 by RA plus LAS. Then IAS multiplied by KT will give TMS, motor torque. Already we derived that TM is equal to KT into IA. Now the TMS here also you can take the transfer function theta m s by TMS is equal to 1 by JMS square plus BMS. So 1 by S I had taken outside. So you put them together, theta ms by TMS is equal to 1 by JMS square plus BMS you will get. And if you want, tap the omega ms, the derivative theta ms, tap it before 1 by S so that you will get that output. Then omega m into KB ECB, you are feeding back. So this set of equation is replaced by this block diagram. Now one simplification. You can neglect the armature inductance effect, LAS, compared to RA. Because yes, the operating frequencies of the motor are quite small, so that the inductive reactance is negligible compared to the resistance of the coil. Hence, you can simply replace here by 1 by RA instead of 1 by RA plus LAS. Now we are applying the block diagram simplification. This is a feedback network. You asked a doubt how physically the feedback system works. Here it is an example, a physical feedback network. Because you understand each and every part of this, that only replaced by this. So physical system is having such a feedback configuration. So what is the net transfer function between theta m and EA? That is theta ms divided by EAS is equal to 1 by S you take outside, that I had taken outside. This alone is G in the forward path, H in the feedback path. So G by 1 plus GH. This G divided by 1 plus GH. Here H is nothing but KB. Take outside. So KT by RA by JMS plus BM is the value of G. So the same formula I am using and can be simplified like this. KT by RA, S into JMS plus BM plus KT KB by RA. Where JM is the moment of inertia of the rotor, BM is the viscous damping of motor bearing, and this KT KB by RA is you can see BM is added with KT KB by RA. BM is a mechanical passive damping, whereas KT KB by RA is also is having the damping units only. It is added with passive damping, but this is due to the electromagnetic induction. For example, if you are not connecting this configuration, if it is not there, suppose you open circuit. I'll give a case. You are open circuiting this, and you are not connecting any EA. It's not driving. It's not connected. Here it is connected to a voltage source. You know that internal impedance of a voltage source is 0. So effectively it is short circuit plus a voltage in series with a voltage driving unit. Now what I'm telling is I am removing the battery. That is simply open circuit. Simply open circuit is equivalently replaced by making RA as infinity. Right? RA is equal to infinity in this expression. So RA will go to infinity means this term will vanish. So it is, the damping is only the mechanical damping. But the moment you close the circuit of the armature, you need not connect any EA, just close it. Then if you try to rotate by hand the motor, you will experience an extra, in addition to the mechanical damping and electromagnetic induction effect. You can call it as electromagnetic damping. That is the additional effort to oppose the generated currents and all. So that is called electromagnetic damping, this additional term. And you might experience this if you are driving a bicycle, riding a bicycle with dynamo connector. Then dynamo as such will have some sort of passive damping effect. But while you are riding, and if dynamo is generating voltage and the voltage is connected to the front bulb and the bulb is producing energy in terms of heat and light, then there is a finite resistance for the circuit, and whatever additional effort while you are applying on the pedal by your legs, the additional energy, mechanical energy, is converted into electrical energy and some heat energy. Now you simply remove the bulb. If you remove the bulb means RA becomes infinity. Suddenly you can understand that the damping will come down. Because RA goes to infinity means this will come down. Understand? So so you might have experienced what is the meaning of electromagnetic damping. Now I am showing another slide. This can be the last slide, otherwise there are some more portions are there, but I will take in the next class. Otherwise, I think now itself you are weird off. We will shift this to next class. That is the next Thursday. The first portion. By Thursday, I will be able to finish it. We will otherwise continuously taking too many hours. Understanding will be difficult. So I will send you this material. You can go through this material, come prepared, and you can ask any doubt on the next class. And we'll finish the theory in the next class, and then probably Friday onwards we can start the lab. Okay.
Okay,
Thank
sir.
you, sir.
I hope all of you have marked your attendance using the answer key, attendance key.
Yes, sir.
Yes, sir.
Okay. Okay. All right. All the best. Take care.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.